Hello friends, good afternoon and welcome to EduSet live lectures. Dear friends, as you know that we have started a series on polynuclear hydrocarbons in heterocyclic compounds, and today we are conducting yet another lecture in the same series. In today's lecture we will try to understand a heterocyclic compound named azoles. We will try to understand its preparation, its properties, characteristics and also its derivatives. To discuss this topic, we have with us our subject expert, Dr. Sushila Singhal. Dr. Singhal is Assistant Professor in Department of Chemistry in Deshbandhu College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you, Ambeji. Good day, viewers. Today we are here to discuss heterocyclic aromatic compounds, azoles. Till now we have discussed the 5-membered heterocyclic compounds containing only one heteroatom. These azoles are the heterocyclic compounds which contains 2 heteroatoms in the 5-membered ring. These are called azoles, and depending upon the second heteroatom, these have been classified. These can be 1,2, 1,3 and 1,4 also. So today we will discuss about azoles introduction, molecular orbital structure of 1,2 and 1,3 azoles, then resonating structures of these 1,2 and 1,3 azoles, basicity of 1,2 and 1,3 azoles. Then we will do the individual members. One of them is imidazole. We will study the imidazole introduction, then its preparation by the action of ammonia on glyoxal, by residue sky synthesis, by dehydrogenation of imidazolenes and from alpha halogenoketones. Then we will study its physical and chemical properties and some biologically active compounds containing the imidazole. Then we will study the next member which contains oxygen heteroatom and which is called as oxazole. We will study its preparation and properties. Then the third member which is called thiazole, and we will study biological active compounds containing these oxazole and thiazole in the second module. So these azoles are 5-membered ring containing 2 heteroatoms. These have been derived from pyrrole, furan and thiophene, which contains only one heteroatom, by the replacement of its CH double bond group, or you can say methine group, by a sp2 hybridized azomethine nitrogen, which is also called as pyridine type nitrogen, at the position number 2 or alpha, or it can be at the position number 2 which is called as beta. So here you can see that we have shown you the 1 and the 2. This is the 1,2 position and this is the 1,3 azole, in which we are having a different heteroatom other than the nitrogen already present. Now depending upon the position of this azomethine, these have been classified as 1,2 azoles. These are the examples of 1,2 azoles. One of them is pyrazole, in which both heteroatoms are nitrogen. Then isooxazole, in which one heteroatom is nitrogen and other one is oxygen, and it can be isothiazole, in which one heteroatom is nitrogen and other one is sulfur. These azoles can be 1,3 azoles. In case of 1,3 positions, if both heteroatoms are nitrogen, it is called imidazole, and if oxygen is present, it is called oxazole, and if sulfur heteroatom is present in combination with nitrogen at 1,3 position, it is called as thiazole. Now comes the molecular orbital structure of these azoles. In azoles, each atom is sp2 hybridized and the pi molecular orbital is consisting of the pz orbitals of the ring atoms. The aromatic sextet of 6 delocalized pi electrons is contributed by 1 electron from each carbon atom and 1 from the azomethine nitrogen, that is pyridine type nitrogen, while 2 electrons are donated from the second heteroatom, similarly as in case of pyrrole, furan and thiophene. The azomethine nitrogen has its lone pair of electron in the sp2 hybridized orbital, which is in the plane of the ring, that is orthogonal to the plane of pi molecular orbital. The lone pair of azomethine nitrogen therefore does not participate in the aromatic sextet and Thus, it makes azoles basic in nature, because this lone pair which is present on the second heteroatom, it is available for protonation, or it can be available for donation to the other atom also. So, it will contribute to its basicity and it will increase its degree of nucleophilic character. Here you can see the molecular orbital structure of 1,2 and the 1,3 azole. This is the 1,2 azole. In case of 1,2 azole, this is the nitrogen and this is the carbon, and this heteroatom is present at the second position of the already present nitrogen. So, it is 1,2. In these you can see these are sp2 hybridized orbitals and 2 electrons are from the second heteroatom, and this is the 1,3 azole molecular orbital structure. Then comes the resonating structures of 1,2 and 1,3 azoles. Here you can see the resonating structures of 1,2 azoles. In the 1,2 azole, these dipolar or these charged structures are present, which will contribute to the main resonance hybrid towards 1,2 azoles, and these resonating structures, these will contribute to the resonating structures for 1,3 azoles. Then comes the basicity of 1,2 and 1,3 azoles. The presence of additional pyridine type nitrogen, that is the azomethane nitrogen with lone pair of electron, it contributes towards the basicity in azoles. The lone pair of electron on the pyridine type nitrogen is not involved in maintaining the aromaticity, but is available for protonation. This makes azoles more basic than 5-membered heterocyclic, which contains only one heteroatom. However, this basicity of azomethane nitrogen is also affected by the interaction with the second heteroatom in azoles, and therefore it depends upon the nature of the other heteroatom and its relative position to the already present heteroatom. So, the second heteroatom, which is X, other than pyridine type nitrogen, it possesses two mutually opposite effects. One of them is mesomerically electron releasing effect of heteroatom, which can be called as base strengthening effect, and another effect is inductively electron withdrawing effect, which can be called as base weakening effect. So, for discussing the position of this heteroatom present, when the both heteroatoms are nitrogen and are present at 1,3 positions, as in case of imidazole, the mesomeric effect, that is the base strengthening effect, is strong and it predominates over the inductive effect. Thus, imidazole is a stronger base than pyridine, but inductive effect, that is the base weakening effect, will predominate if the heteroatom is oxygen or sulfur, which are having the powerful inductive electron withdrawal capacity, and thus it will reduce the basicity of oxazole and thiazole. Here you can see in the equation that this is the azole, this is 1,3 azole. After protonation, it will form this cation, which is inductive electron withdrawal will destabilize this cation, and mesomeric electron releasing effect will stabilize this cation, and if both are nitrogens, then it will be more basic, and if this X atom is oxygen or sulfur, it will reduce its basicity. Further, when both the heteroatom are nitrogen and now they are present at 1,2 positions, the inductive effect will predominate over the base strengthening effect and it will reduce its basicity. Moreover, the base weakening effect will increase with oxygen and sulfur also, and it will cause further reduction in its basicity. So, whether nitrogen is present or oxygen or sulfur, it will reduce the basicity of 1,2 diazole. Now, the one of the individual member of azoles is imidazole. This is type of 1,3 azole in which both heteroatoms are nitrogen. Imidazole or imidazoline is an azopyrrole, a planar compound in which the nitrogen atom is separated by one carbon atom. Earlier, this compound was called as glyoxylene, as it was first prepared from glyoxal and ammonia in 1858. Its benzoyl derivative is called as benzyimidazole. The imino nitrogen is assigned position 1, while the tertiary nitrogen is given the position number 3. This is numbering has been done in the imidazole structure. This nitrogen is having the carbon number 1 and from the right side 2, 3, 4 and the 5 carbon. Here is the structure of benzoimidazole. Here also the numbering will start from the imino nitrogen and it will go with the tertiary nitrogen atom, then it will go to the benzene ring. Now comes the synthesis of imidazole. Imidazole can be prepared by the action of ammonia and glyoxal. So first of all, this is a glyoxal molecule. It will react with water to form formaldehyde and the formic acid. A mixture of aldehyde and acid is prepared. Then this formaldehyde will react with glyoxal in the presence of ammonia. These all three will condense together, will cyclize together to give us the imidazole ring by the removal of 3 molecules of water. The next synthetic method is Redis-Zewski synthesis. This is probably the most important synthesis of imidazole. It consists condensing a dicarbonyl compound. It can be glyoxal, it can be alpha ketoaldehyde or it can be alpha diketones with an aldehyde in the presence of ammonia. Here in this case, in this reaction, we have taken benzyl. This is a benzyl molecule. It reacts with benzaldehyde and ammonia with the 2 molecules of ammonia. These condense with each other to give a cyclized product and will finally yield the 2,4,5 triphenyl imidazole. So from this reaction we can get the substituted imidazole. Imidazole can be prepared by treating paraaldehyde with bromine in ethylene glycol and heating the resulting product 2-bromomethyl 1,3-dioxolone with formaldehyde and ammonia. Here we have taken the acetaldehyde which first will undergo bromination to make its alpha bromoacetaldehyde which react with ethylene glycol and will cyclize first, then will react with the formamide in the presence of ammonia and will finally give us the imidazole ring. Imidazole is best prepared by the action of ammonia on a mixture of formaldehyde and tartaric acid dinitrate, which can be called as dinitrotartaric acid. This is the dinitrotartaric acid. First it loses 2 molecules of nitrous acid and makes this compound which on reaction with ammonia and formaldehyde cyclizes to give a product which is a dicarboxylic imidazole which on heating will reduce 2 molecules of carboxylic acid or you can say will undergo decarboxylation in the presence of copper at 300 degrees centigrade and finally will give us the imidazole ring. Imidazole can also be prepared by the dehydrogenation of imidazolines. These imidazoles have been prepared by imidazolene in the presence of sulfur. However, a milder reagent, barium magnate, can also be used in replacement of sulfur. These imidazolines first obtained from the alkyl nitriles and 1,2-ethanadiamine. This is the 1,2-ethanadiamine. First it will react with alkyl nitrile and will condense to give us imidazolene. This imidazolene will then react with the milder reagent which is a barium magnate and will finally give us the imidazole ring. Next synthetic method is from alpha halogenoketones. This method involves the interaction between amidine and alpha halogenoketone. Here we have taken phenyl acyl bromide and benzyimidine. These 2 molecules will condense together and will lose 1 molecule of water and 1 molecule of hydrogen bromide and will finally give us 2,5-diphenyl imidazole product. Similarly, amidine can also react with acyloin or alpha halogen ketone to yield us imidazole. Here we have taken alpha bromoketone. This is the alpha position of the ketone, so it is alpha bromoketone. It will react with this amidine molecule and will lose 1 molecule of water to make a unstable intermediate which will immediately lose one molecule of hydrogen bromide and one molecule of hydrogen and will cyclize immediately to give 4,5 dialkyl imidazole nucleus. Further, the next derivative of this imidazole, or you can say higher member of this imidazole, that is the benzimidazole, is more important than this imidazole. As the former member or imidazole, it occurs in vitamin B12, that is a thiamine. 1,2-diaminobenzene, this is 1,2-diaminobenzene, it condenses with a carboxylic acid. On heating will lose 2 molecules of water at 100 degrees centigrade and it will give us a benzimidazole. It is very important compound. The cyclization of N-haloamidine with sodium ethoxide also forms benzimidazole, which is followed by a nitrene intermediate. First of all, nitrene intermediate is formed, which is, since it is a intermediate, reaction intermediate, so its stability is less, it is almost unstable, and it immediately converts into its higher member, that is the benzimidazole. Now comes the physical properties of imidazole. Imidazole is a colorless liquid with a boiling point of 256 degrees centigrade and is high boiling than all other 5 membered heterocyclic compounds. In marked contrast to imidazole, the boiling point of methyl imidazole is comparatively low. It is because of hydrogen bonding exists in imidazole ring which do not have any substituent. It undergoes hydrogen bonding and up to 20 molecules of imidazole in aqueous medium makes a hydrogen bonds, and since hydrogen bond is stronger bond, so its melting point raises, boiling point raises. Imidazole is more basic with a pKa value of 7.2 than pyridine, which is having a pKa value of only 5.2. It also shows amphoteric properties and behaves as an acid also, because it contains pyrrole type nitrogen in the ring and it forms metallic salts with sodamide and RMGX, which is a Grignard reagent, which are exclusively hydrolyzed by water. Further, the introduction of alkyl groups or any electron releasing group in the ring increases the basicity, since it will increase the electron density on the nitrogen which is available for its basicity cause. Imidazole is an aromatic compound and is possessing a resonance energy of 14.2 kilojoule per mole. The dipole moment of imidazole has been measured in several solvents. In dioxane, the value is 4.8 dBi. This large value indicates a considerable polarization in the imidazole ring, which have been shown from the resonating structures of imidazole also. Now comes the chemical properties of imidazole. It can react with acids. Imidazole is a monoacidic base and it forms crystalline salts with acid. It also possesses weakly acidic properties which can be called as pseudoacidic and is even more acidic than pyrrole and forms salts with the Grignard reagent and with the metal ions of the following type. Here you can see that this imidazole, it accepts a proton and it makes a resonating structures of these two salts. Here also it reacts with Grignard reagent to form imidazole magnesium chloride. It can undergo quaternization reaction. Quaternization of imidazole at nitrogen atom is normally achieved by the reaction of alkyl halides or dialkyl sulfates under strongly basic conditions in an organic solvent, while in water the yields are very low owing to the strong water solubility of the reaction product. Since the reaction product is soluble in water, so the yield of the reaction will be low. Alkylation of imidazole can be made by heating 1-carboxythoxyimidazole, which is obtained by reacting imidazoles and ethyl chloroformate. The representation of the reaction can be seen from this slide. These imidazole, it also undergoes electrophilic substitution reactions. The contribution of these charged structures of imidazole are more important than those of benzene also. For this reason, imidazole possesses increased reactivity towards electrophilic attack. It is more susceptible to attack than pyrazole or thiazole also, and is more even than from furan and thiophene. From the resonating structures of the imidazole, we can see that we have shown here the attack on the carbon number 2. If electrophile will attack at carbon number 2, we will get these 3 resonating structures. Out of these 3 resonating structure, this resonating structure is less stable because it is having a double bond and a positive charge on the nitrogen atom. While if attack will take place at carbon number 4 and carbon number 5, we will get the resonating structures which are almost stable. So, the attack will take place at C4 and the C5 positions. For the electrophilic substitution reaction, halogenation of imidazole is very complex and varies considerably depending upon the substrate, depending upon the reagent and the reaction conditions also. Bromination with bromine in chloroform will yield 2,4,5 tribromo derivative. Although we are saying that the electrophilic substitution will take place only at the 4 and the 5 position, but it also depends upon the reaction conditions also. And if these 2 positions are already occupied, then it will go to the position number 2 also. Iodination can also take place in the alkaline medium to give us 2,4,5 triiodoimidazole. Further nitration and sulfonation can be afforded at the carbon number 4 and the carbon number 5. It will not take place at carbon number 2, since if it takes place at carbon number 2 and this sulfonic acid group is a bulky group, so it will create a steric hindrance in concern with the nitrogen atom already present. So, sulfonation will take place either at the carbon number 4 or at the carbon number 5. Then imidazole also reacts with oxidizing and reducing agents. Imidazole itself is very stable to auto-oxidation and to the action of chromic acid, but is attacked by potassium permanganate. Oxygen in the presence of sensitizer will act as singlet oxygen and will react to give an imidazoline derivative. So, this is the imidazoline. It will react with oxygen in the presence of sensitizer and in the presence of methanol. It will make a unstable state which will convert immediately into a cyclized state, which on reaction with methanol will give us 4,5-dimethoxy 2-imidazolidione. So, oxidation will take place. Potassium tridichromate, a milder oxidizing agent, can be employed for the oxidation of allylic and benzylic alcohols to their corresponding carbonyl compounds. Imidazole can also react with nucleophilic agents. 1,3-azoles in general do not react with nucleophilic reagents unless any electron withdrawing groups are present. A halogen atom in the carbon number 2 can be replaced by the nucleophiles such as alkoxy, thiols and amino alkyls and some others. Of a nucleophilic attack result in the ring fission, ring breaks in the nucleophilic attack. In particular, amino-imidazoles are unstable owing to heterolytic cleavage, and quaternary imidazole salts decomposes to primary amines in the presence of alkali when the classical Schotten-Bowman method is employed to prepare benzyl imidazolines, the ring cleavage to yield the 1,2-dibenzamidoethene. Here you can see in the reaction, we have taken the imidazole ring, which will first react with benzoyl chloride to give its chloride salt. Here the hydroxy nucleophile will replace the halogen atom present at the carbon number 2 and finally will cleave the ring, and we will get a ring fission in the product, and finally we will get here 1,2-dibenzamidoethene. So, in case of nucleophilic attack, we will get a ring opening in this case. Further, imidazole catalysis of ester hydrolysis. Imidazoyl group of an histidine residue may be implicated in the mode of action of such hydrolytic enzymes as that of trypsin and chymotrypsin. Imidazole has been used as a catalysis of ester hydrolysis. Two pathways can be there, a general base catalysis and a nucleophilic catalysis. In general base catalysis, the imidazole molecule, it functions as a base. Here you can see in the structure, this is the imidazole ring. It will act as a base towards the water molecule and it will activate this water moiety, which will attack on the carbonyl carbon of the acyl compound. So, this is a kind of ester hydrolysis in which this imidazole ring will catalyze the ester hydrolysis. The second pathway is the nucleophilic catalysis. In this catalysis, this imidazole ring will directly attack on the carbonyl compound of the acyl compound and it will follow a intermediate position and finally it will catalyze the ester hydrolysis. The next important property is the cycloaddition reaction. Imidazole undergoes addition across the carbon-carbon double bond under photochemical conditions. The reactions of imidazole with the benzophenone and acrylonitrile will give us the cycloaddition product in the sunlight. This is the imidazole ring. It will react with first benzophenone in the presence of benzene and sunlight. It will give us this cycloaddition product. This is in the second structure, in the second equation, you can say this is a substituted imidazole. It will react with acrylonitrile in the presence of sunlight and it will also give us a cycloaddition product. Then comes some naturally and biologically active compounds. This imidazole is incorporated in many important biological molecules such as purines, xanthine, guanine and coenzymes also. It is widely distributed in essential amino acids in L-histidine and its derivatives carnosine, which is a dipeptide and is a constituent of mammalian tissue. Here you can see this is the structure of L-histidine and here is the structure of carnosine. This histidine amino acid is present in many proteins and plays a vital part in the structure and the binding functions of hemoglobin. Histidine can be decarboxylated to histamine, which is also a common biological compound. A number of synthetic imidazoles such as Priscol, Privine and antihistamine, they also have physiological properties. There are more industrial application of imidazole also. It has been used extensively as a corrosion inhibitor, especially for prevention of copper corrosion. And many its industrial application is in photography and electronics also. Synthetic imidazole are also present in many fungicides and antifungal, antiprotozoal and antihypertensive medications. It is present in anti-cancer medication mercaptopurine, which combat leukemia by interacting with the DNA activities. So, there are many industrial application of imidazole. It is a very important azole compound. This was all about the imidazole. Thank you. Now, after completing the first member imidazole, we will start with the second member, which contains the other heteroatom oxygen, then nitrogen. It is called as oxazole. Oxazole is a 1,3-azole having an oxygen atom and a pyridine type nitrogen atom at the 3 position in a 5-membered ring. These oxazole they doesn't occur in nature, so they doesn't play any part in the fundamental metabolism of a human body or a plant system. It is considered to be derived from furan by the replacement of methine group from the position number 3 by the azomethine nitrogen. The interest in the chemistry of this oxazole was developed after the World War, when penicillin was considered to contain the oxazole ring system. Further, 2,5-diaryl oxazole are also used as fluorescent whitening agents because of their scintillating properties. So, oxazole are also important. Partially reduced oxazoles are called as oxazylene, and 3 types of possible structures are there, isomers are there, depending upon the position of the double bond. These are 2-oxazolene, 3-oxazolene and the 4-oxazolene. Here you can see the structure of these 3 isomers, and this 4th structure is a fully saturated system of oxazolene. It is called as oxazolidine. These oxazolidines are solids and behaves as bases and are readily hydrolyzed by water. Since there is no aromatization, so the lone pair present on the nitrogen are freely available, so these act as bases. Then comes the synthetic methods of oxazoles. Oxazoles can be prepared from ethyl alpha hydroxy ketosuccinate. This method involves reaction between the ethyl alpha hydroxy ketosuccinate and formamide to give us diethyl oxazole 4,5-dicarboxylate at 100 degrees centigrade, which on reaction with barium hydroxide in the presence of water will undergo hydrolysis to give the carboxylate, which on further reaction with quinoline in the presence of copper will reduce 2 molecules of carbon dioxide, or which will undergo decarboxylation to finally give us the oxazole nucleus. The second important method of oxazole preparation is Robinson-Gabriel synthesis. It is a cyclodehydration method. It involves cyclodehydration of alpha acyloaminoketone in the presence of dehydrating agents, which can be sulfuric acid, phosphorus pentachloride, phosphoryl chloride and thionyl chloride. The reaction proceeds via an intermediate with the formation of C5 and oxygen bond. So, here this is the reactant of the molecule. It will undergo cyclodehydration. Here water will go out from this position, and this C5 and this oxygen bond will be formed in the cyclization process, will finally undergo removal of water and will give us the oxazole ring. These oxazoles can also be prepared from isocyanides. Reaction of alpha metallated isocyanides obtained by treating isocyanides with N-butyl lithium or potassium tertiary butoxide. This is the metallated salt of this isocyanide. It will react with carboxylic acid derivative. This is the carboxylic acid derivative, that is the acyl derivative of carboxylic acid. These together will react and will make a intermediate, which will rearrange to give a cyclized product, which after the removal of mineral acid, that is the hydrochloric acid, will finally give us a substituted oxazole ring. These oxazole can be prepared from alpha amino carbonyl compounds. This method consists of refluxing an alpha amino carbonyl compound with an amino ester to give an oxazole. This is the amino ester. It reacts with alpha amino carbonyl compound. In the presence of acetic acid, it will undergo refluxing, that is simultaneously heating and cooling the both two reactants together, will give us the intermediate product, which will lose a molecule of ammonia and will rearrange itself, will cyclize together to give us a substituted oxazole, which is a 5-methyl 2-phenyl oxazole. These oxazole can be prepared from acyl aziridines, which is a ring transformation reaction. Here you can see that is a 3-membered ring is transforming into a 5-membered ring. Thermolysis of one substituted 2-aryl 3-phenyl aziridine, this is the reactant of the molecule, it will give rise to 2-aryl 5-phenyl oxazole in high yields. The reaction probably proceeds via an azomethane halide, an intermediate, which is obtained by a heterolytic cleavage of a carbon-carbon bond of the reactant. The carbon-carbon bond of the reactant has been broken and the halide cyclizes to oxazolene, which on oxidation will finally lead to oxazole. So, here ring has been transformed from 3 carbon to 5-membered ring. Next important method of preparation of oxazole is Pomeranz-Frid's synthesis. It involves the cyclization of benzyl amino acetals in the presence of phosphorus pentachloride or sulfuric acid. If nitro group is present on the ring, then exclusively oxazole is formed in this reaction. These oxazole can be prepared from 1-benzoyl triazoles. Here we have taken triazoles, 3 nitrogens are present in the same ring. Oxazole have been prepared from pyrolysis of these triazoles, these substituted triazoles by flash vacuum pyrolysis. Here sigmotropic rearrangement from nitrogen to carbon has been done in this reaction and it will convert into a first a ring opening is there and then this ring opening will finally make a substituted oxazole ring. Here we will get 5-phenyl oxazole in this reaction. Then the next member, that is a fused member with the benzene ring, is the benzo-oxazole. These are usually prepared by heating 2-aminophenol, this is 2-aminophenol, it reacts with derivative of carboxylic acid in the presence of boric acid. In case of carboxylic acid, there should be a good leaving group present in the carboxylic acid. It will reflux together to give an intermediate product which will then cyclize to give benzo-oxazole. Now comes the physical properties of oxazole. Oxazole is also a liquid with a boiling point of 69 degrees centigrade and has an odor resembling to that of pyridine. It is miscible with water and many other solvents also. It is weakly basic with a pKa value of 0.8, but it is more basic than isoxazole, which is a 1,2-azole. The dipole moment of this oxazole has been measured to be 1.5 dBi. Although it possesses a sextet of pi electrons, but the complete delocalization is restricted due to the presence of electronegative oxygen atom and up to some extent the nitrogen atom also. Then comes the chemical properties of oxazole. One of them is electrophilic substitution. Oxazole is more reactive towards electrophilic substitution than thiazole, but less than imidazole. The preferred attack is in the case of other 1,3-azole, it will take place at 5 position. We have done here the bromination. Bromination of 2-phenyl oxazole will result in the 5-bromo-2-phenyl oxazole. So, here the bromination will take place at the carbon number 5 and we will get the 5 substituted oxazole. The next substitution reaction is mercuration. Mercuration of oxazole with mercury 2 acetate in acetic acid will occur at C4 or C5 depending upon the available unsubstituted position. If both the positions are already substituted, then mercuration will take place at the carbon number 3. Here we have taken 4,5 diphenyl oxazole, already 4th and the 5th positions are occupied. It will react with mercuric acetate, and so here in this case the substitution will take place at the carbon number 2 and we will get 2 substituted oxazole. Then comes a Diels-Alder reaction of oxazole. the introduction of the second heteroatom does not affect the diene nature of oxazole, and thus not expectedly oxazole behaves similar to furan in case of Diels-Alder reaction. The adduct so obtained are more important precursors for the preparation of pyridine or furan derivatives by the loss of appropriate fragment. Here you can see in the reaction, this is the oxazole and it is a dienophile. These will together make this adduct which will undergo appropriate fragmentation to give us a pyridine molecule and a substituted oxazole. So, Diels-Alder adduct will then further react or will lose some molecules, will condense to give some another molecules. These oxazole can also react with nucleophilic reagents. Since oxazole ring is electron deficient with lowest electron density at the position number 2, the cleavage of the oxazole ring by nucleophiles is rather a more frequent reaction than nucleophilic substitution. The nucleophile will cleave the ring instead of doing the substitution on the ring. Oxazole, when treated with ammonia or formamide at 200 degrees centigrade, will involve an attack of nucleophile at the position number 2 and transformed into the imidazole by a cleavage of oxazole ring. First the ring will cleave and then it will transform again to give us a different product or a different azole. Here oxazole is converting into a imidazole by a nucleophilic attack. First of all, this ammonia will attack on oxazole and ring opening is going on, and we will get a ring opened alicyclic product which will then lose water of molecule and will react with ammonia, will lose a molecule of ammonia and finally will give us a substituted imidazole. These oxazole, these also reacts with oxidizing agents. Oxazole ring is not stable to oxidative conditions and is opened by the action of oxidizing agents. For example, cold KMnO4, chromic acid and ozone also. Oxazole is stable to the action of hydrogen peroxide. Here ring cleavage will not take place, it will not affect the ring structure, but 4,2-oxazoyl pyridine with hydrogen peroxide in acetic acid will finally give the pyridine N-oxide derivative. So, here the oxidation will take place in the pyridine ring and we will get here the oxidized product, that is the N-oxidized pyridine derivative. Oxazole also reacts with the reducing agents. Oxazole remarkably stable towards the variety of reducing agents, but on reduction of the ring we will get the oxazolidine with sodium in ethanol. 2,5-diphenyl oxazole on reacts with lithium aluminium hydride and THF tetrahydrofuran will give us a 2-benzyl amino 1-phenyl ethanol. Here also ring has been cleaved and we will get an long chain product. These oxazole, it also undergoes photochemical reactions. Oxazole undergoes photochemical isomerization when it is irradiated with ethanol or in benzene, giving a mixture of photoisomers. The reaction proceeds to involve the ring contraction, ring expansion mechanism and the electrocyclic mechanism. So, 3 type of different mechanisms are going on simultaneously: ring contraction, ring expansion and the electrocyclic mechanism. Here you can see that this is the oxazole which on reaction with ethanol in the presence of sunlight, here 2 isomers, photochemical isomerization is taking place and we will get here from 1,3 to 1,2-azole. 1,3-azole is converting into 1,2-azole. And here you can see that we are getting this adduct on photochemical reaction. These oxazole can also undergo cycloaddition reactions. These exhibit diene type characteristics and undergoes Diels-Alder reaction with alkynic and alkylic dienophiles involving interaction of the highly occupied molecular orbital of the oxazole and the lowest unoccupied orbital of the dienophile. In case of Diels-Alder reaction, diene-dienophile type of interaction goes on and we will get the adduct. So, here in this case also, in case of oxazole, we will get here a adduct of diene-dienophile. Here you can see in the reaction that this is the oxazole molecule, it will react with the alkene, substituted alkene, and we will get here the adduct. Further, these oxazole are also present in some naturally active compounds which are biologically active. Although the occurrence of these oxazole is rare, but naturally occurring oxazole, it includes some alkaloids. One of them is pimprine, which is isolated from streptomyces pimprina. This is the structure of the molecule, structure of the alkaloid which contains the oxazole ring. Oxazole derivatives are also known to have anti-inflammatory, analgesic, antibacterial and antiviral properties. 2 amino azoles are useful as hypertensive agents. So, this was all about the oxazole. Now, the next member is a thiazole. In thiazole, we are having the second heteroatom, which is a sulfur in combination with the nitrogen in a 5-membered ring. The thiazole ring system contains 1,3 position of nitrogen and sulfur, and it is present in many natural products. It is structurally related to thiophene and pyridine, but in most of its properties it resembles with pyridine. The numbering of the thiazole starts from the sulfur. Sulfur will get the number 1, then second 2, nitrogen will get the number 3, and then the 4 and the 5 carbons. The reduced thiazoles serves in the study of polypeptides and proteins and occurs as structural units in compounds of many biological importance. These are the 3 reduced thiazoles. These are the partially reduced isomers of thiazoles. One of them is 2-thiazoline. This is a 3-thiazoline, and the last member is a 4-thiazoline. We can also get a fully saturated thiazolidine isomer also. Now comes a synthetic method of thiazole. Thiazole can be prepared from alpha halocarbonyl compound. This method involves interaction of thiamides and alpha halocarbonyl compounds. For this reaction, we have taken here chloroacetone. This is the chloroacetone. It reacts with thioacetamide, and these two molecules will interact together and will give the 2,4-dimethyl thiazole. In this reaction the yields are very less since these two side products are there. Thus thiazole itself, this is the substituted thiazole, we can get the thiazole, pure thiazole itself, which can be prepared from chloroacetaldehyde. This is the chloroacetaldehyde molecule. It reacts with thioformamide, and these two molecules interact together to give a pure thiazole ring. Here also the side products are there, which is hydrochloric acid and water. So, in this case the yield is low. Thiamide for this purpose can be obtained by reacting phosphorus pentachloride and formamide at room temperature. For this formamide, this is the formamide, it reacts with phosphorus pentachloride, and we will get here the thioamide, which reacts in the previous reaction. A possible mechanism for this reaction could involve the stepwise elimination of water and the hydrochloric acid. Since both are the side products, so they will be eliminated through the mechanism. Here in this case, this thioamide, it will attack on the carbonyl compound of the chloroacetaldehyde. In this manner, it will attack on the carbonyl compound, and we will get this intermediate state, and from here this OH and H will go as a water, and we will get here the cyclized product. Then from the nitrogen, hydrogen of hydrogen which is attached to the nitrogen, and this chlorine will go as a hydrochloric acid, and we will get here the thiazole. So, this is a probable mechanism of this reaction. Thiazole can also be prepared from alpha thiocyanoto ketones. These alpha carbonyl compounds and metal thiocyanate react to give alpha thiocyanate to ketone, which cyclizes on treatment with either acid or with the alkali and will give us 2-hydroxy-4-methyl thiazole, which can be obtained from chloroacetone and barium thiocyanate. So, here in this reaction you can see the reaction. In this reaction, first these two reactant will interact together and will lose one molecule of sodium chloride and will give this intermediate product, which will undergo hydrolysis to give us the hydroxy derivative, which will then cyclize and will finally give us 2-hydroxy-4-methyl thiazole. So, substituted product can be formed from this reaction. The next important reaction of preparation of thiazole is Gabriel synthesis. This synthesis involves the heating of acyl amino compounds with the phosphorus pentasulfide, yielding thiazole derivatives. The carbonyl group is probably attacked first by the phosphorus pentachloride, the oxygen atom being replaced by sulfur, and then the intermediate will cyclize to thiazole. So, here you can see this is a di-keto derivative. First it will react with the phosphorus pentachloride and one of the oxygen has been substituted by the sulfur, which is a unstable state. It is a resonance hybrid of two state. It is a reversible state, and since it is unstable, it will lose a molecule of water and it will cyclize immediately to give us 2,5-dimethyl thiazole. Then comes the physical properties of thiazole. Thiazole is a colorless liquid with a boiling point of 117 degrees centigrade. It also resembles with pyridine in its odor and it is miscible with water. It is also weakly basic with a pKa value of 2.5 and it behaves as a tertiary base. Thiazole rings are planar and aromatic also. The alkyl derivatives of thiazoles are more basic, for instance 2-methyl thiazole and 4-methyl thiazole. Since in case of alkyl derivative, alkyl groups are electron releasing groups, so they will increase the electron density on the nitrogen atom and will give the contribution towards the basicity of the molecule. Then comes the chemical properties of the thiazole. Thiazole, since it is a base, it can also react with acid to form the salt. So, reaction with the acids, the lone pair of electron on the azomethyl nitrogen is not involved in aromatic sextet and is thus available for protonation. Thiazole as a result form stable crystalline salts with strong acids. The presence of electron releasing substituent at the carbon number 2 increases its basicity considerably, while the electron withdrawing substituents at the carbon number 5 will causes its reduction in its basicity. Then comes the electrophilic substitution. The reactivity of thiazole in electrophilic substitution is well documented. The reactivity is intermediate between the pyridine and the thiophene. The attack preferably takes place at the carbon number 5, that is at the position number 5. In acid media, the attack usually takes place through the formation of thiazolinium cation. First this cation is formed, then we will get the substituted product. Thiazole itself is resistant to bromination. However, if electron donating group are present, then bromination occurs readily and very easily. Thiazole can be brominated directly in the gas phase, but in this case 2-bromothiazole is obtained instead of getting 5-bromothiazole. Here in this reaction you can see that this thiazole reacts with bromine at 200 to 450 degrees centigrade in the gaseous phase and will yield a 2-bromothiazole. We are getting here a 2 substituted product, although we are saying earlier that we will get here a 5 substituted product in case of electrophilic substitution. Then comes the chlorination. 2-chlorothiazole can be obtained by treating 2-thiazolone with phosphorus pentachloride. Sulfonation can also be achieved under drastic conditions in the presence of mercury acetate as catalyst. Here you can see in the reaction, this is the thiazole. It will react with mercury sulphate at 200 degrees centigrade, and we will get here a 5 substituted product, that is thiazole 5 sulfonic acid. We won't get the 2 substituted sulfonation product, since sulfonic acid is a bulky group. So, it will reduce the substitution at the carbon number 2. Then comes a reaction with nucleophilic reagents. In thiazole ring, the position 2 is with lowest pi electron density and is therefore more susceptible for the nucleophilic attack. However, the reaction of nucleophiles with thiazole, it requires either activation of the thiazole ring or either we require the strong nucleophile. So, one of the conditions should be fulfilled in this case. The quaternization of the ring nitrogen considerably enhances the reactivity of the thiazole ring towards the nucleophilic attack at the C2 position. Thiazole can be eliminated in the presence of ammonia, as in case of Chichi-Babin reaction, and here we will get the 2 substituted thiazole product. Thiazole can also undergo oxidation reaction. Thiazole ring is relatively resistant to oxidation, but the thiazole substituted with activating groups can be oxidized to an oxidized derivative by hydrogen peroxide or peracetic acids. Then comes the naturally occurring biologically active compounds. Thiazoles and thiazolines are structurally component of a number of peptide derived natural products. Among them are many antibiotic, that is cyomycin, thiostrepton and micrococcin. Anti-tumor antibiotics are also available in which thiazole ring is there. Zadot's novel dicarboxylic amino acid, which is obtained from the mushroom, the botanical name of that is Hierocomus subtomatosus. From this we can get a amino acid derivative which also contains a thiazole, the main nucleus. Then another important naturally occurring thiazole is thiamine, which is a B12 vitamin, in the form of its pyrophosphate in the coenzyme of a number of biological reactions which involved the carbohydrate metabolism, that is cleavage of carbon-carbon bond adjacent to the carbonyl group, as in case of pyruvic acid. It occurs widely in plants and especially in eggs, in the yeast and rice polishing also. The deficiency of this thiamine, this vitamin B12 in diet, it causes the disease which is called as beriberi. This vitamin B12, it also contains this important thiazole ring. So, this was all about the naturally occurring biological compounds which contains these azole rings. Now comes few questions based on this azoles topic. What are azoles? How these are classified? How molecular structure of 1,2 and 1,3 azoles has been assigned? Explain the basicity of azoles and some synthetic methods of imidazole, oxazole and thiazole, and what happens when oxazole it reacts with oxidizing and reducing agents, and you can write about some biological activities of these azoles rings. Thank you.
Dear friends, on that note, we would like to thank Dr. Singhal for coming to our show and delivering this wonderful lecture. And thank you, dear friends, watching our show. Stay tuned and keep watching. Thank you.